So first, like the target audience for this talk. If you're familiar with like cocoons, filtered limits, it's not for you. The purpose of this talk was originally the target audience were my coworkers who were very recently just plain Java programmers, didn't have much clue about what Scala is and how to deal with it and what's a monad, and they were totally like puzzled by all these new terms. So I prepared this talk, and I believe this is how you, hello?
Could you get closer to the mic? Make it closer. It's right in front of you.
This one. OK. How about now? Like this?
Yeah, that should be good.
OK. Do you hear me now? That's what it was. So if you are familiar with these things, which is functor, monad, applicative functor, it's not for you. But if you feel vague, and there are lots of like vague and wrong notions and explanations being spread around the world, so I want to dispel that fog. So that's the purpose of this talk, just to be strict, specific, and clear. So if you write in Scala, you know you have parameterized types, right? So a type can have one parameter, two parameters. It can have like a weird parameter which is also parameterized, and so on. So you can write something like new age, whatever. So this way you can pass any parameter to your type, and so suddenly your type is not exactly a type. It's something that depends on other things. So it's like a function. Take a type, return another type. So we expand this and find specific cases of these parameterized types that satisfy certain requirements that are very, very good from mathematical point of view and from programming point of view. So functor. Functor is a type we provided with a map function. So map depends, like, see, we have a trait f, and it depends on type x, but map depends on another type, y. And map takes a whatever function from x to y and produces a value. The result would be a value of type f on y. So now f maps types, like take a type x and returns, gives us a type f of x, but also it has a mapping from functions to functions. So here we have we have a function f, and we produce a value f of y. So for this mapping of functions to give us a functor, we need two properties. One, these functions preserve identity, meaning if f is an identity from x to x, the result is also an identity. And it also should preserve composition. So I write this, and then you probably know what I mean. We apply f to a function, to a value, then apply g to the result of applying f. So like in more verbose mode, it says like apply f and then apply g. So the result of mapping would be this. Apply map of f and then apply map of g. And map of identity is identity on f. So you know examples, list, right? Or set. So if we have a value s, which is a set of like 3 strings, so s is what is by default is immutable, right? And it's serialized like this. It's displayed by REPL like this. And we map this s with this function that takes a string and take the first element of the string. So with that first, well, strings are sequences in Scala. So it just takes not the first element, but the segment consisting of one character. So the result would be we take all values of s and produce what? A, string A, string A, string A. But we have sets. So A is equal to A and is equal to A. So the result would be just set of consisting of just one string, A. So see, it's not like element to element producing like from initial values the result values. We have still an instance of a set. Well, the fact that the result is still string is not essential. We could as well take like drop 1 and then transform it to numbers, so we would have numbers like 1, 2, 3. So what's essential is that we had a set and we produce a set, and it doesn't have to be one-to-one correspondence. So we had functor defined like this: map preserving composition and identity, right? So if we have two functors, their composition is also a functor. So if we map f using g and then map f using f, so the whole operation is taking an f of g of x and producing f of g of y. So suppose we have a set of lists of strings and we transform those strings to integers. So as a result would be a set of lists of integers. So we do that mapping, but that mapping goes inside. So that's how it is. That's why it's a functor. And for it to be a functor, it also should preserve composition and identity. To see that composition is preserved, like the first component does preserve it, and then the second also preserves it. So the composition does preserve it. And the same with identity. Both are preserved step by step. So that's it about functors. But not everything is a functor. Here's a funny example. Define E, just a parameterized type, on X, like this. Like a type of functions from X to X. There is no way you can define mapping from X to Y. Like given a function from X to Y, you cannot define a mapping from X to the power of X to Y to the power of Y. No. Not everything. I can say that that's because of variance breakage. Like one argument is covariant, another is contravariant, but we are not going there. Of course, functors, like in science and math, they can be covariant functors, contravariant functors. I'm only talking about covariant, and let's not go into variance. So, but variance is the explanation why this is not a functor. Well, variance is like this, but we can just kind of almost ignore it. So f of plus x meaning we have map as I showed before, right? For instance, list of strings is a subtype of list of lists of objects, and list of objects is a subtype of any, list of any ref. When I'm saying subtype, meaning we talked about a different kind of mapping, right? Subtyping mapping. So it's a special kind, but when you talk covariance in Scala, we talk about only this way of mapping. String is an object. Object is any ref. Any ref is any. But for functors, you have to preserve this mapping. Map should work for any function. So sets, I showed recently that it's a functor. But it's not an easy thing, because if we talk about relationship between type and subtype, set is not exactly a functor in this sense. So here we have some kind of problems. And there was a lot of argument and discussion on Scala about like whether set is contravariant, whether set is covariant, and whether it's invariant. Currently, the current belief is that set is invariant. But in which sense? In the sense of subtyping. So if we have a set A1, A2, and A3, and we do this mapping of identity, okay, it works, right? But, so S. So we'll have a set of any, right? And we apply identity. So that's a wider mapping using functions. But if we try to use mapping using just subtyping relationship, wow, somehow it doesn't work. type mismatch. And of course, a set of strings is not a set of any's. If it were mutable, we could add an any. Well, it's a known Java problem, right? If you convert a set of strings to a set of any's, how you can add a number to that? But in Java, we'll have a runtime exception. Scala kind of doesn't allow us this. Having functors, we have map, right? So it allows us to use this syntactic sugar and have this kind of, use that mapping and produce these things. Like I would scan over the list of these numbers, probably prime numbers, right? G would run over the list of hellos, and we map this. It's being transformed into map that will call this on all these values. So it's a map inside map that this. But well, here we are just printing it. So this, I believe there was a talk about for loops right before these talks, right? So okay, so I'll be fast. So instead of printing, we could produce a list of pairs like this string and int by yielding this G and D by scanning the first list and the second list. And map is behind the scenes, and it gives us, well, that's what we have. We have list 1, and we map that. And we have list 2 inside, where we map the things inside list 2 into this pair. So the result would be the list of all the possible pairs. Or is it a list of lists? Yeah. It's tricky. So we are getting closer to monads, but we're not there yet. So that was all about functors. Now, applicative functor. Applicative functor has a little bit stronger feature than a regular functor. So what's an applicative functor? For an applicative functor, like we have an f, f is our functor, right? We have a mapping, we are given a mapping, it's called app, from the type x arrow y to the type f of x arrow f of y. So if we had a list of functions, we can map a list of x's, whatever, into a list of y's. How? We have like 10 functions, we have 10 numbers. So how many results we will have? Probably 100, right? So that's what app does by default. But there are other ways. We can zip them. I'm not going there. Alternatively, instead of this, we can redefine applicative functor like this. Because our category is Cartesian closed. We can redefine it instead like this. Call this method and also define an x and y and map pairs x and y into f on pairs. So we have a list of x's and a list of y's, and we produce a list of pairs x and y. And why is it possible? Well, because we do just carrying or uncarrying. In this case, we do uncarrying and get this one. So having this definition and this definition, they're equivalent. Like we have having a list of two functions, f and g, and a list of numbers 1 and 2. So the first way, using app, we produce functions and numbers. We produce a list f applied to 1, f applied to 2, g applied to 1, g applied to 2. So these are all possible combinations. Or using this, and also we fold these things, or zip these things, fold. Like having A and B, probably strings, right? Or whatever values A and B are. We have two lists, and we produced a list of all possible combinations.
There's water for you there, Vlad.
Yeah? Oh, yeah, yeah, sorry. Yeah. So if you have a list of lists, it's a typical thing that you need, you want to flatten a list of lists. Like in many cases, you have a code that produces option of options of options, or list of lists of lists, and in a more like tricky cases, option of list or set of lists or list of sets, list of options. And you have to somehow simplify that code. The simplest solution is you have a list of lists, right? And if you like this 4, magically you produce just a list of its elements. It's flattening of a list. So a monad is what allows us to do flattening. A monad is a functor that has flatten features and has a unit. A unit, given a value, it produces an instance. Given a value of type x, it produces an instance, a value of type fx. For instance, like if it's a list, it's a singleton. If it's an option, so it will be something. And flatten is when you have a list of lists, you flatten them. When you have an option of options, you flatten them. But we should not think that monads are always containers. That's a popular belief, and it's not true. I mean, it's not always true. So, but what we need in a monad, we need these features, these properties, and we also need some features. Like flatten deals correctly with units, and flatten double flattening if you have f, 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 x. So you can do flattening inside, or you can do flattening outside, doesn't matter. If you have a list of lists, right? So you can first flatten the list outside and produce a list of lists, and then flatten again and produce plain list. Or you can do, for every element, apply map of flattening and flatten the list inside and then flatten again. So for a monad, it should be the same thing. Again, like what's flattening for list? Well, if I have a list like this, list consisting of list 1, 2, and 3, and empty list and 4, 5, 6, the result of flattening would be this. And this is the unit, right? A singleton list. A popular alternative definition of monad is through Flatmap. From like categories point of view, what's Flatmap? Apply map and then flatten. So that's what it does, right? So we instead of like rewriting them separately, suppose we have some data that are of different type. So first we do mapping, and then we flatten it. So like take all the people probably in the world and have a list of, and for each person list all of the person's cells. We don't have those lists yet, but maybe like sometime in the future. And so this way we'll produce a list of all cells of all humans. And the operation is behind the scenes. Like if you were here and listened to Dick, that's how it's represented. Like when desugared, we take list of all people and flat map with the function called list cells. And why this flat map works properly? Because it's a monad. So here are monad laws. If M is a monad, then we have unit, we have flatten, and if we have apply unit to flattening, we have a monad, take a unit, so we'll have MM, right? Unit adds one more M, wraps it. Like if we have a list, it gives a singleton. So we apply unit to MX and then flatten. It will be the same MX. And if we have MX, like list of lists, right? And if we map it on MMX, like inside, so if we do flattening inside, and then so we'll have MMX, and then flatten again. It's the same as if we were flattening outside. So this way, if we flatten this M with this M, we'll have MMX, right? And flatten again, the result is the same. Here's an example. List of A. And we can flatten in both ways. I talked about this already. So examples of monad. Lists. Well, you encountered lists. You know how to flatten lists. List of lists, and it works, right? Sets. A set is a monad. So if you have a set of sets, how do you flatten it? Union. That's it. What's a unit for set? Singleton set. Option. What's a unit for option? Sum. What's flattening? If you have option of options, so you can do using, like you can either use flatten, or you can use like Flatmap with identity, or you can write a case match like empty or sum, and then produce just one option. Option of option you can easily convert into plain option. So result, I'll skip result, stream, future, all the things have that flattening. So with try, I believe you can, well, why I skip result? Because that's my class, so I'm not talking about my class today. So what do you do with try? You can match the try with success or failure. And if you have a try and try inside. So in case of failure, you have a failure. In case of success, what's inside? If we have a failure inside, so it's failure. If you have a success inside success, so we extract that success and we have just single success. And nullable, interestingly, it's a little bit like, that's basically coming from Java. But in Java, we can also look at this. Like, if it's null, so we don't need to like denullify, dereference it. If you have something and that produces a null, so you don't need to call the function. So that's why people in Java always check for null. They do this monadic, these monadic operations without knowing what a monad is and what a functor is. They're just used to it. So again, monad is not a container. Here's an example. Like take a state monad that keeps state in the left, and we throw it this dice. Well, because it's a monad, state is a monad, right? So we can, it has map, because a monad is a functor, and it has flat map. So we can throw dice twice, throw here. Well, the result would be what we threw like after 2 times, so we'll have these 2 numbers. Start with a known seed and do this. This is a function, 2 dice. Throw dice 2 times. The result of throwing will be a pair of integers like this or this. But it's not exactly what that. It's not a container. It doesn't contain anything. You throw again and the result would be totally different. So it's just something that keeps the state but changes it on every throw. So how about composing 2 monads? Like we have one monad, a list, and another monad, like a set. So can we know that the composition of 2 functor is a functor. So that's cool, right? Monads are not that good. The problem is we need the flattening, right? So we have monad G and monad F. And apply again G and then F. Can we flatten it to F of G? Generally speaking, no, because see, we could flatten F with F to F. We can flatten G with G to F. But how can we do this transformation, like swap G and F to F of G? No way. Can we transform a list of sets into a set of lists? How? We have like set ABC and then set 1, 2. What list do we produce? We don't know. We can probably go the other way, like we have a set of lists and we can try all combinations, yes. But list all elements of a list of sets, so it's, well, it's hard to tell what exactly it is. So list of futures and future of lists. It works one way, but it doesn't work another way, and I wouldn't say I know which way it works. Yeah, well, this we can do, right? So we can like wait until all the things, all these futures finish, right? But if we have a future of lists, can we transform it into a list of futures? Well, hardly, and it's definitely not efficient if we even invent that. No, it's not possible. Like if we have a future of lists, right? So should we like wait for each individual element, keeping in mind that there is something else? So all these components of the list will depend on other components. So it's impossible. So lists with features don't commute. So that's why in languages like Haskell, Scala, whatever, people invented tons of so-called monadic transformers. So they invent like, here the transformer. So having a list of sets, we produce by this transformer a set of lists. Or having a set of lists, we produce by this transformer a list of sets. Yeah, but we have to keep in mind, they are not given to us by default. They're not given us for any possible combination of monads. So you saw that applicative functor before, right? That had like this interesting feature. We can transform pairs into pairs of values of functor into a functor on pairs, or we can transform a function into another function. Some monads are also applicative. There is a belief that, like in some categories, in some languages, every monad is applicative. Well, that's a bad belief because it really depends on pretty like tricky features of that language, and once you change the language a little bit, kaboom, it will break. It's not so in categories in general settings. You can look it up on Math Over Flow, I guess. So not every monad is applicative. But if it's applicative, if it's an applicative functor, it's called strong monad. And what's good about strong monad? You can run them in parallel like this. So suppose we have this, suppose ask name is something like that better than option. So it either returns a name or returns a description, like a result class, returns a description of failure because of this and that, so it's like try. And suppose, well, try is not applicative, but suppose there's another function SSN that also either returns a good result or returns failure. And we can do this also on that stuff. Why we can do it? Because it's applicative. Because this monad, we built it strong. We have this operation and also for the monad. Generally speaking, a monad doesn't have that. So in this case, we can write this kind of loop. And the whole loop is like this. We find name in SSN. Then probably we find the company name. And we produce a new employee with this name, this SSN, and this company. What happens if we couldn't find a name? We'll return an error saying that, oh, couldn't find a name. But if we found SSN, it's OK. If we couldn't find name and SSN, if we couldn't find a name, and if we couldn't find SSN either, the result of this and also will produce us two error messages. Name isn't found, name not found, SSN not found. That's how compilers work. A compiler that you run doesn't give you the first error and then fails, right? It shows you all possible errors because it works like this. And also, we try to do as much as possible. So we run these things in parallel, ask name and ask SSN, and we try to return both results. If we are successful, then the next, that's monadic thing. The next operation is extract company name. I don't know where company name comes, but we could as well fail on company name. If we succeeded here and failed here, we'll have only one error. Oh, no company. But if we failed here, like on both name and SSN, we will not bother to go for company because that's flattening in option or result class will not go deeper, will not call it. We already have a failure. So this is a combination of applicative features and monadic features in this loop. Well, some monads are naturally applicative, like list. Well, because you can zip. Like here, we have a bunch of functions and a bunch of whatever values, and we yield f of x. So we don't have to guess. List. Actually, if you look closer, there is not a unique way to turn a monad applicative, even if you can turn. For lists here, we'll have all possible combinations of functions f and values x, right? Another solution would be to zip, like take the first function and the first value. Take the second function and the second value. There's a puzzle, or what do you do when like the first list ends before the other list ends? So in Haskell, they kind of bypass this by generally like expecting a list to be potentially infinite. So they produce some solutions, but in Scala we don't do that. Scala is not Haskell. But again, if instead of lists we had streams, yeah, we could zip streams together. That's okay. So meaning applicativity, monadic strength, is not given to us by default. It can vary. So it's up to us to choose what to use. So that's it. Thank you. Questions? Should I go back to the first slide? So, like, functor, type with a map, applicative functor. We have this mapping, or alternatively, we have an also that converts Cartesian product with f on Cartesian product. Monad is a functor with flattening in units, and strong monad is an applicative functor that is also a monad. That's it. So these are the definitions, and we can like look through them and basically not pay attention to those like additional stuff. Yeah.
You mentioned monad transformers. Can you talk a little bit more what's the purpose of monad?
Yeah, monad transformers. So,
Vlad, would you repeat the question?
yeah, the question was, can I say a little something about monad transformers? Since not every two monads produce after composition a monad, we have to find a way. We may find a way to make it a monad. So how do we make it? Look at this, like FG, FG. We want to transform it to FG, right? For that, if we're only lucky to have FFGG, then FF flattens to F, GG flattens to F, and that's it. But the thing is, here we have this like something that breaks our commutativity. FG inside, GF inside. So if we had a transformation from GF to FG, then we are lucky, right? We have FG, FG, transform the thing inside into FG, so we will have FFGG, and then we flatten them individually. So this thing, transformation from GF to FG, is called monadic transformer. So for any given pair, like there should be probably like a big table somewhere. Monadic transformers for all combinations, like option of lists to list of options, or list of options to options of list. Set of futures to future of sets. Well, that's hard. Or future of sets to set of futures, and so on. So all these things, they're kind of a popular topic. And people come up with, well, as soon as you invent a monad, right, you have to figure out how my new monad can interop with lists. How can I deal with sets? So it's a typical thing that, like, especially for new programmers, so they produce this stuff like, oh, we have like cool list. Oh, but I cannot write this for, because I cannot transform. You cannot write like a for loop where the first element is a set and the other one is option. Well, option is iterable, so it transforms to iterable. So iterables you can flatten. But if you have the first row as a list, and then like state monad, or like those dice throwing, or not state, but like future. So we would be puzzled. How come I don't produce the right result? So that's a typical question by Java programmers. Your monads are not good because I cannot like convert a list of sets of futures to a future of sets of lists. Yes, you cannot, because that's the laws of nature. That's not the problem of monads. That's like a Rubik cube. You cannot like turn one side and then the other, and then one back and the other back and produce the same thing. That's 3D. That's the properties of the space where we live in. Yes?
Could you give the most surprising example of using some of the advanced context in your practice, like applicative functor or
Yeah.
Monads?
Yeah, so the question was, can I give like a nice example of using applicative functors? So this is basically what, like in the previous company, in health expense, in my current company, I use Java 6, excuse me. So what we do, we like open a web page and try to extract data from there. So the data are EOB, explanation of benefits. So we look up like patient name, patient date of birth, like claim number, the amount, and so on. And we look that stuff up. If we find everything on the web page, this is okay, like we process it and that's good, we're good. But what if something is not found? We cannot just like throw into the logs something not found, right? Well, people do it all the time, like in Java specifically. But here I want to have the list of all the failures, so we can say, patient name not found. Or maybe like we found the patient, but we have 5 patients with the same first and last name. David Smith, probably. Or like date of birth, well, found but wrong. Well, I have to confirm, I'm not working there anymore, so we have 20 people born born during the days of Julius Caesar. So meaning like the first 2 digits of the numbers are missing. So all these things, they can be listed because we have a class called result. So result is either good with the value, or maybe like some values, or it can be bad with the list of failures. Those failures actually also contain stack trace. So you can, like, if you are really curious about like what's going on, so you can dump stack trace of all these errors that happen. So instead of just ask name and ask SSN, we have like a bunch of these things. Also, we can have a list of these. Like we've tried to get like value number 1, value number 2, and so on, value number n. So there is this thing called traversable. I believe Adalbert was talking about traversables like 2 talks before, right? So we traverse it, and we either produce a list of good values, or we produce a list of error messages. So that's another feature of applicative functors. You can traverse it. So that's what we did successfully. A bunch of Java programmers got into it, and I remember hearing them saying after like 2 or 3 months switching from Java to Scala, I want to write stuff in monadic style. So that's how, like, if you provide good tools and explain these things, they will be doing it monadic style, and it's pretty efficient. Basically, the purpose was to make sure that we don't need so many developers, but we need the staff work, like I don't know how many, 400 servers, right? Something like that. Yeah. Yep. Anything else? So I would say like it was successful in our company. Thank you.